Welcome to C4.1.3 Halogen Displacement Reactions. So our lesson objectives for today are to describe the displacement reactions involving group 7 and then be able to explain whether a displacement reaction is going to occur based on the combination of the different halogens. So before we start this, we need to review what we did in the last lesson, C4.12, when we looked at the halogens. When we looked at the halogens, we found out that the group 7 elements get less reactive as you go down the group. So what this means is that fluorine at the top of the group 7 is more reactive than chlorine, which is more reactive than bromine, which is more reactive than iodine. And this is going to be important when we talk about our displacement reactions. So we need to bear this in mind. So before I get on to the chemistry, we're going to have a look at a model of this using food. So I want you to imagine that you've got 5 pieces of food that listed in order of how much you like them. So whatever you've got like the most goes at the top of the list, and whatever you like the least goes at the bottom of the list. So on the slide I've listed mine. So chocolate's at the top and gherkins at the bottom. So if I was eating pizza, which is kind of in the middle of my list, which means I quite like it, but there's a lot of things that are nicer than it. So imagine I was eating pizza. If somebody comes along and they offer me some chocolate or crisps, which I think are nicer than the pizza, then because I think it's nicer than the pizza, I'm going to put my pizza down and I'm going to eat my chocolate or my crisps instead. However, if I'm eating my pizza and somebody comes along with peanuts or gherkins that I don't think are that great, then I'm going to continue eating the pizza, and I'm just not going to touch the peanuts and the gherkins. So we can use this as an analogy for what happens with halogens. So when I was eating my food, if someone offers me nicer or more attractive food, I'm going to put down the less attractive food and eat the nicer food. However, if I'm eating food and somebody offers me something that's less attractive, so worse food, in my opinion, then nothing's going to change. I'm just going to continue as I am. So this is the same for halogens. So if you've got an element that's formed a compound of a halogen, if a more reactive, so instead of attractive, a more reactive halogen comes along, then that element's going to react with a more reactive halogen and form a compound with that. However, if an element's formed a compound of a halogen and a less reactive halogen comes along, then nothing's going to change. There's not going to be any reaction. So if we look at the chemistry of this, so remembering our order that fluorine is more reactive than chlorine, which is more reactive than bromine, which is more reactive than iodine. So as we've just discussed, a more reactive halogen is going to displace a less reactive halogen from a compound. So we call them displacement reactions because the more reactive halogen takes the place of the less reactive halogen in the compound. So in this equation here, I've used X and Y for our halogens, and M is just metal. So if you look at that equation there, then the X2 is going to be the halogen elements coming in, and My is going to be the metal halide compound. So it's going to be a compound that's formed from a metal reacting with a halogen, and that's going to be a metal halide. So that reaction is only going to work if X2, so the halogen which is just an element, if that halogen that's an element is more reactive than Y, then you will have a reaction. If X is less reactive than Y, then you're not going to have a reaction. So here's a couple of examples. So if I have fluorine reacting with sodium chloride, then because fluorine is more reactive than chlorine, it's going to displace the chlorine in the sodium chloride, and we're going to end up with sodium fluoride and chlorine. And that works because the fluorine's more reactive than the chlorine. However, if I had, again, sodium chloride, but this time I had bromine, which is less reactive than chlorine, there's not going to be a reaction. So nothing's going to happen, nothing's going to change, because the bromine's less reactive than the chlorine, and therefore the sodium stays with the chlorine. So we can show this by doing a practical, which obviously I can't do online. But here's the description of what you would do in the practical. I'm not going to read out the exact instructions, you can read that for yourself, but I'm just going to explain generally what's going to happen. So the diagram at the top left is a spotting tile, which we've used in lesson before. So you would place some chlorine, bromine, and iodine solutions in the spotting tiles. So the chlorine water is just chlorine dissolved in water, bromine water is just bromine in water, and iodine, again, is just iodine dissolved in water. So you put those in your spotting tiles, and then you would add some potassium chloride, potassium bromide, and potassium iodide to those tiles. and then you would see whether there's any change. So to one row you have chlorine water, another row you have bromine water, another row you have iodine, and then in column 1 you would put potassium chloride, in column 2 you'd put potassium bromide, in column 3 you'd put potassium iodide, and then we would observe what happens. So we're looking for any colour changes that are going to happen. So here are the expected results if we did this practical in the lab. So remember that chlorine's more reactive than bromine, which is more reactive than iodine. So as you go down that table, the halogens are becoming less reactive. So no visible change means no reaction is going to happen. So anyone where the halogen's the same, so chlorine reacting with potassium chloride, bromine with potassium bromide, iodine with potassium iodide, there's not going to be a reaction there because it's the same halogen, so you will not see any visible change in that. With chlorine and potassium bromide and chlorine and potassium iodide, because the chlorine is more reactive than the bromine and the iodine, you're going to get a displacement reaction. So the chlorine is going to react with the potassium bromide to give potassium chloride and bromine. So what you will see is the bromine forming. So you'll see a yellow-orange colour as the bromine forms. And for the potassium iodide with chlorine reaction, you would see a brown colour appearing because iodine is going to form. So for the bromine reacting, bromine's less reactive than chlorine, so nothing's going to happen. Bromine's not going to react with bromine. And bromine is more reactive than iodine, so when you get bromine and potassium iodide, you're going to get a brown colour appearing because of the iodine forming. Iodine is the least reactive of these three, so in none of them are you going to see any change. So there's going to be no visible change or no reaction for all of those three. So you need to be able to name the products of the reaction. So for chlorine reacting with potassium bromide, it's a displacement reaction. The chlorine takes the place of the bromine, so you end up with potassium chloride. The bromine in the potassium bromide ends up just becoming the element bromine. So it's going to give you potassium chloride and bromine. If you have chlorine reacting with potassium iodide, it's going to be potassium chloride and iodine. And then lastly, if you have bromine reacting with potassium iodide, you're going to get potassium bromide and iodine. Thank you for listening.